Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think yesterday we were discussing about the Haworth synthesis of anthracite. And anthracene, as we know that it has a molecular formula C14H8 and the structure is represented over here. If you count the number of carbon atom, you will find there are the 14 carbon atom, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So number of hydrogen atom is each corner like this. Here one hydrogen atom because 3 bond already there, so 1. But here there is no hydrogen atom because this satisfy all the valencies are there 1, 2, 3 and 4 and therefore there will be no hydrogen atom. But here 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. There are the 10 hydrogen atoms are there. Sorry, here make the correction C4 and H10. So C14, let us 6, 7, 8, 9, 10, 11, 12, 13, 14. In my previous lecture there are the 8. So remember the molecular formula of anthracene will be C14H10. And we talked about the Haworth synthesis of anthracene, and the starting material he has taken is a benzene and one of them is a naphthalic anhydride, and very famous reaction, that is a Friedel-Crafts acylation reaction. Acetyl group is introduced. This part is known as acetyl. So in presence of the Lewis acid catalyst AlCl3, and as we know that the function of Lewis acid catalyst to generate the electrophile, and this benzene is a nucleophile, this is the electrophile reaction carried out, and we get this is an intermediate. This carbonyl group is going to convert into a hydrocarbon. There is a suitable reagent. They have used zinc amalgam in presence of HCl in acidic medium. Reaction takes place, that is known as a Clemenson reduction. You might have heard in a basic medium there is a what we can call it as a Wolff-Kishner reduction, but here the acid groups are there. With that base it will affect or impact on it, and therefore whatever the desired product you won't get suitably like this, and therefore in acidic medium Clemenson reduction played very important role for the conversion of carbonyl group into as this one hydrocarbon. And now there is a cyclization. HF is a cyclizing agent which can be used here. Just by heating it you will get as this type of the compound. There is a carbonyl group over here. We require to remove it or convert that carbonyl into as a hydrocarbon, we will get as this compound. Again the same reagent is using here zinc amalgam in presence of hydrochloric acid, that is a Clemenson reduction, and after complete conversion of carbonyl group into as a hydrocarbon, then they brought the aromatization into it by using the reagent, very good reagent, selenium or palladium in presence of chalco. Heating we will get as a anthracene. So that type of the description we have described in our previous lectures. Now we are going to discuss about the reaction of anthracene. That is the point which we are going to discuss here. Let me clean the board first and then we will discuss about the reactions of anthracene. That is the point which we are discussing over here. So here reactions of reactions of anthracite. Reactions of anthracite that we are discussing about. And as we know that anthracene is a tricyclic compound, right? Anthracene commonly undergoes aromatic electrophilic substitution reaction, which is the one of the important characteristic of aromatic compound. In addition to that, radical substitution and 4+2 cycloaddition reaction, ninth position of anthracene is more reactive because of stabilization of sigma complex. So why 9th position of anthracene is a more stable? Only one sentence answer, because when you show the mechanism when that pi bond form as a first one is the sigma complex, that sigma complex is more stable due to the resonance. And as we know that number of resonance structure goes on increasing, the stability of that organic compound goes on increasing. On the same basis, there is a formation of sigma complex, and that sigma complex will be the most stable one, and therefore this anthracene commonly undergoes as aromatic electrophilic substitution reaction, radical substitution, and 4+2 cycloaddition reaction. 4+2 cycloaddition reaction in photochemistry or in a pericyclic reaction, you might have heard these 4+2 cycloaddition. Cycloaddition reaction means two substrate. 4 means diene system and 2 means enone system. There are the two systems generally present over there. For example, so like this is a diene and there one is a diene. One is a diene and this is called as a ethylene, and or it is known as a dienophile. Diene is a diene and is a dienophile. The diene is a nucleophilic in nature, whereas dienophile is a act as an electrophile, and this reaction is generally termed as 4+2 cycloaddition reaction. And how it reacts? This double bond is going to attack at this terminal. This double bond shifted here and this double bond is utilized. So there is a cycloaddition reaction. Pericyclic reaction means movement of electron in a cyclic manner. They are the concerted reaction. They are a highly stereospecific reaction, and we are going to get the end product will be this one. This is a cyclohexene. This is obtained as a cyclohexene. So one of the compound is obtained over there. They are reversible reactions. And then we can call it as a retro-Diels-Alder reaction, or it is one of the famous reaction, Diels-Alder reaction. It is known as a Diels-Alder reaction. Diels-Alder reaction. That is a 4+2 cycloaddition reaction, and he discovered, and that's why name is given to that as a Diels-Alder reaction. This is a Diels-Alder reaction, and backward is called as a retro-Diels-Alder reaction. So that the reaction and 9th position of anthracene is more reactive because of stabilization of sigma complexes. Now let us see structure of the anthracene. As we know that 3 benzene ring fuse together by sharing the 2 carbon atom equally and 3 benzene ring are fused together. This is known as the structure of anthracite. Now, how to give the numbering system for anthracene? Starting from here, can remember 1, 2, 3, 4, then 5, 6, 7, 8, 9 and 10. That is a general naming system or numbering system is followed or used in anthracene. Look at here, in naphthalene is a different way, but here 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Middle one is a 9 and 10. So this 9 position is a more reactive 9 we can say, or because after the electrophilic substitution reaction occurs, then what is going to happen when electrophile is attacking at this, let us see here, electrophile when attacks at this position, suppose, what is going to happen? This electrophile I am showing here as and then it is attacking like this. So what is going to happen? So you are going to get, this is this type of the compound I am showing over here. Suppose let us see, this is a bond over here, other bonds remains as it is. Now here electrophile I am attacking. Now when here is a positive charge over there, is sigma complex. Now this sigma complex, this is a, or you can call it as a sigma complex over here. Sigma complex. With this sigma complex positive charge present at that position, look at here the bond 1, 2, 3. Tertiary carbocations are there. And this tertiary carbocation is more stable, and as we know the stability order of the carbocation, primary, secondary and the tertiary, and therefore this is a more stable. This sigma complex formation is a more stable in this case because it gets stabilized. This double bond, if you show the resonating structure, how would you show this? This double bond is shifted from here to here and you will get the another structure maybe like this. So I am showing as only as a one structure over here, and other structure you can show by here. The double bond positive charge comes over here, then this double bond will shifted from here to here. You will get another resonating structure over here. Positive charge comes here, then this goes there, then likewise you can show the resonating structure of that compound. So this is a sigma complex. Why? 9 position of the anthracene is a more reactive. The reason behind it is a stabilization of because of the stabilization of the sigma complex, and which I have tried over here to represent that how sigma complex are formed over here. Now let us see the most readily they undergoes as a electrophilic substitution reaction, and that I am going to show over here. See the electrophilic substitution reaction shown by that anthracene, because anthracene is a aromatic compound and therefore it shows the reaction. One is a nitration here. Nitration reaction. As we know that nitration, the nitro group can be introduced by using as a nitric acid, as we know that when anthracene is treated with concentrated HNO3 and acetic anhydride at 50 to 20 degrees centigrade gives a mixture of 9-nitroanthracene and 9,10 dinitroanthracene. when the reaction will be carried out in presence of concentrated HNO3 and acetic anhydride, as we know that AC2O, or simply we can write here CH3, C double bond O, C double bond O, and CH3. Acetic anhydride, this one. And this AC, this shortly it is known as a acetyl group, AC. And that's why it is generally represented by AC2O. Nitration reaction will be here. And now, when the anthracene will be treated with concentrated HNO3, as we know that concentrated HNO3 in presence of acetic anhydride, and the temperature is kept 15 to 20 degrees centigrade, somewhat lower than the room temperature generally in India. And in a winter season, the temperature is room temperature maybe as a 15 to 20 degrees. So you can carry out this reaction after the addition of that concentrated HNO3. The reaction takes place and the product will be obtained as a mixture of the product generally is getting over here. So I think, let me show that properly so that we can show that clearly. Here the anthracene I am showing over here, 3 rings like this, double bond, and as we know that this middle one is a 9 and the 10. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. This is a numbering system. When it is treated with, let me show clearly over here, concentrated HNO3, nitric acid, HNO3 in presence of acetic anhydride AC2O, and the temperature is kept around 15 to 20 degrees centigrade, the product will be the mixture of the product. They had got one is this one I am showing, as well as another product I am showing over here. Still I think we have not getting as enough space. Let me once again over here. This is the one structure which I am trying to draw over here. Another structure, this one. So this is now it's enough space. Look at here, double bond I am putting this manner, in this way. Now my 9 position is here, so nitro group is introduced over here. This is a nitro group. So 9 nitro anthracene, 9 nitro anthracene, 9 nitro anthracene, that is the name of that compound we got over here. Now in case of the second structure, we can also get nitro group at 9 position as well as nitro group at 10 position, and therefore we can call it the 9, 10. 2 nitro groups are there, therefore we can call it as a dinitro-anthracene, dinitro-anthracene. That is a product which we are getting over here. Look at this, is our starting compound is anthracene. Anthracene, that is our starting compound. Numbering systems are used like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When it is treated with concentrated HNO3 in presence of acetic anhydride, temperature is kept 15 to 20 degrees centigrade. The resulting compound obtained will be the mixture. One is a 9-nitro-anthracene and another one is a 9,10-dinitro-anthracene. These are the two products, and more than two products are formed. There is a problem of separation. If one is in a solid and one is a liquid form, then it is very easy to separate. If that solid compound does not dissolve in the liquid, whatever the liquid compound form during this reaction. And so if there are the different technique used to separate mixtures of the organic compound from each other by using as a different technique, and that technique I think yesterday I already discussed that one. Now let us see the another reaction, that is a sulfonation, and one of the another reaction which is carried out, because we are discussing the reactions of anthracene. Let me show the another reaction here which can be, because we are talking about the reactions of aromatic, polynuclear aromatic compound. Poly means many, nuclear means that cyclic, you can call it as more than two cycles are formed. So here tricyclic is anthracene, and where these are the aromatic compound, and aromatic compound has a tendency to undergo electrophilic substitution reaction readily, such as nitration, sulfonation, halogenation, Friedel-Crafts, alkylation, acylation. So second one we are going to discuss here is a sulfonation. The sulfonation, for this sulfonation we generally using the reagent, that is a concentrated H2SO4 in presence of acetic acid, as we know that CCOOH, or you can write as a ACOH, either this way or this way. There are the different ways to represent that acetic acid. Generally we are writing that CH3 C double bond OH. Here acid is a, why it is acid? After the dissociation it produces as a H, and that's why it is acidic in nature. Sulfonation. Generally anthracene react with concentrated H2SO4 in presence of glacial acetic acid. Glacial means pure acetic acid. Gives a mixture of alpha and beta anthracene sulfonic acid. Similar to as a naphthalene, in anthracene also has two positions, 1 and 2 position. Sometimes it is referred as alpha and beta positions. So let us see here sulfonation reaction once again. See here, this is a structure which I am representing over here. This, the structure of anthracene. This is the structure of anthracene. When it is treated with concentrated H2SO4, H2SO4 in presence of acetic acid, CH3COOH. What do you get? You are going to get the mixtures of the product. Let me draw that product here. Another structure which I am showing here like this. See, the anthracene aromatization will be maintained here, the double bond. Now the sulfonic acid group will be introduced at SO3H. This is a sulfonic acid. So this is known as alpha anthracene sulfonic acid. Alpha anthracene sulfonic acid. And second one, that SO3 group be attack at this position, that is SO3H, and which is known as the sulfonic acid group is introduced at a beta position, and therefore you can call it as a beta anthracene sulfonic acid. Beta anthracene sulfonic acid, right? One is alpha anthracene sulfonic acid, another one is a beta anthracene sulfonic acid, and we are again getting as a mixture of product with that sulfonic acid. And as I already told you that when the mixtures are obtained, there is a problem of separation. So this is one of the way of getting alpha anthracene sulfonic acid and the beta anthracene sulfonic acid. In addition to this, if you use excess of concentrated H2SO4, 1,8 sulfonic acid and 2,7 sulfonic acid are formed. If you use the same reaction when carried out, here we are using as a equivalent amount of the starting material and the reagent, we are end up with this kind of the mixture we are getting. But if you use as a excess amount of concentrated, let me clean this first so that you can clearly observe that reaction, or you can see that reaction. Now I am showing once again second possibility here, the structure which I am representing, that is anthracene. This is a structure of anthracene, right? Now when it is treated with excess amount of concentrated H2SO4 in presence of acetic acid, CH3COOH, what would be the product? And the product generally gives you 1,8 disulfonic acid and 2,7 disulfonic acid are formed. Look at here, 1,8 sulfonic acid is the one structure which I am representing here, you can see clearly. Another structure I am representing over here, you can see clearly over here. Now the numbering system which is using here 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Now the first 1,8, 1 is here, so nitro group is introduced at this position, and 8 here NO2 group is present, so we can call it as a 1,8 dinitro, sorry, not nitro, here is a not nitro, sulfonic acid. That's so here SO3H, here also is SO3H. That is at 1 and 8 position sulfonic acid is there, and therefore we can call it as 1,8 disulfonic acid, disulfonic acid. Or in the other way round, we can get this mixture also at 2,7 position. Here is a 2 position where SO3H group is introduced, and 7 position, where is the 7 position? Here, right? Here is a 7 position SO3H. Means this you can call it as an alpha position, and these you can call it as a beta position. That's the way. And you can say this is a 2,7 disulfonic acid. 2,7 disulfonic acid we generally getting after the excess use of concentrated H2SO4 in presence of acetic acid, how it gives is reaction, so that excess of concentrated H2SO4 in presence of acetic acid, while predicting as a product, then you should remember. How do you remember this 1,8 disulfonic acid? Because at 1 and when you are using as the excess amount of concentrated H2SO4, these 1 and 8 position are alpha position, and 2 and 7 are the beta position. So in a previous example we have seen, when we using as a same equivalent of starting and the reagent, we are getting or leading a mixture of the product alpha and beta, right? So alpha anthracene sulfonic acid, and another mixture is a beta anthracene sulfonic acid. Or either we can say 1 anthracene sulfonic acid and 2 anthracene sulfonic acid. That's the product which we are getting over. So I think these two reactions we have discussed here in this particular lecture. So in next lecture or in upcoming lecture, we will discuss the remaining reaction like halogenation, Diels-Alder reaction, means cyclization, and then oxidation reaction, Friedel-Crafts, alkylation, Friedel-Crafts acylation, that type of the reaction. On that anthracene we will see in our next lecture. Till then, have a nice day. Thank you.